The Digit Recognition System, CIS579 Artificial Intelligence Term Project by Kirilo Crisco. The Digit Recognition Project focuses on the development of a neural network model to recognize handwritten digits. This is a classic problem in the field of machine learning and serves as a great introduction to the concepts of neural networks. The task is to train a model on available for free dataset of handwritten images and save model to a file to correctly identify digits from custom JPEG images. We use the NIST dataset, which contains 42,000 training images. We split dataset into two portions, 1,000 images for validation and the rest for training. Each image is grayscale and 28 x 28 pixels. The data for every number stored in CSV table as rows. The first columns represents label, actual number, and other 784 column stores float values for each pixel of the image. The Digit Recognizer is a standalone Python application. The main window provides UI for training model with custom parameters, alpha and iterations, displays numbers image, random nose initially, allows user to select custom JPEG for recognition and perform actual recognition. Once loaded the first time, the user can train and save the model with the Train Model button. The application will perform model training displaying every 10 iteration accuracy. With 500 iterations, we achieve an accuracy of 85%. The model will be saved as a set of CSV files in the application data model folder. Once we are happy with the model, we can test the results on the validation portion of the NIST set. Enter the MNIST index and press Recognize Image Number. The 128 row contains data for number 5. The image from the NIST set will be shown in UI, and the prediction displayed in the status line, MNIST number 5 recognized as 5. The Load Image button allows the user to submit a custom image. The custom image is shown in UI and a prediction been made. Here we get to number 3 from the application Data Custom Images folder recognized as 3. Custom number 3 recognized as 3. The application sometimes can make a wrong prediction. For example, custom number 1 is recognized as 2, which is expected considering the 85% accuracy. Our model is a two-layer neural network, an input layer, a hidden layer, and an output layer. The input layer has 784 nodes, 1 for each pixel. The hidden layer has 10 nodes, and the output layer has 10 nodes, 1 for each digit 0, 9. The system uses forward propagation to compute the output of the neural network, given the input data and the current parameters, and backward propagation to compute the gradients of the loss function with respect to the parameters. Forward propagation is the process of taking an input, an image, and running it through the network to get a prediction. The input layer takes the pixel values, normalizes them, and then passes them to the hidden layer. The hidden layer applies weights and biases to these values, and then applies a RealU activation function. The output layer applies another set of weights and biases, followed by a softmax activation function to get the final output. Backward propagation is the process of adjusting the weights and biases of the network based on the error of the prediction. This is done using a method called gradient descent, which iteratively adjusts the parameters to minimize the error. The loss function used in this model is the cross-entropy loss function. Gradient descent is the method used to adjust the weights and biases of the network during training. The RealU activation function is used for the hidden layer, introducing non-linearity into the model. The softmax activation function is used for the output layer, ensuring that the output values can be interpreted as probabilities. We use matrix and vector operations to perform calculations on all training examples at once, rather than looping over them one by one. This is a more efficient way to implement the model, especially when dealing with large datasets. The model parameters, weights, and biases are learned during training. These parameters are initialized randomly and then updated through gradient descent during training. Through this project, I built a neural network model that can recognize handwritten digits with high accuracy. This serves as a foundation for more complex tasks in image recognition and machine learning. This project provided valuable experience in the development of a machine learning application, from the initial design and implementation to the testing and evaluation of the system.